Hey, welcome back. In this video, we're going to continue discussing the cop versus robber game on graphs. We're going to focus on this optimization problem for the game called throttling, where we're trying to minimize the sum of the number of cops that we use and the number of turns that it takes to capture the robber. Now, when throttling was originally defined for the cop versus robber game, the researchers who defined it bounded the throttling number for many families of graphs, and they observed that for all of the families that they investigated, the throttling number had an upper bound of big O of square root of n, where n was the order of the graphs. For example, for paths, the throttling number had a big O of square root of n upper bound. Same with cycles. Same with any tree of order n, and any unicyclic graph of order n. And unicyclic, I just want to note what that is. These are connected graphs with a single cycle. So like acyclic means no cycles, unicyclic means one cycle, but it's also connected. And here's a problem for you to think about. Prove that the throttling number of the path of order n is theta of square root of n. So in the last video, we saw an argument for the upper bound on the throttling number of the cycle of order n, at least an outline of an argument. And you can imitate that to get the big O of square root of n for the path. So that will be similar to last video. For the big omega of square root of n lower bound, something that might be useful for this is pigeonhole principle. But I'll let you think more about the details of that one. So one of the families of graphs that we mentioned on this slide are unicyclic graphs. And you can actually see that with unicyclic graphs, their throttling numbers, the maximum that they can go is not going to be much higher than the maximum that trees of the same order can go. So we can define this function t of n, and it'll be the maximum possible throttling number of any tree of order n. And it's pretty simple to prove that for any unicyclic graph of order n, its throttling number is going to be at most t of n plus 1. So the highest that a tree of order n can have is the throttling number. A unicyclic graph of order n, its throttling number can only be 1 more than that at most. And the basic idea here is that we take any unicyclic graph, and for the purposes of the robber, we turn it into a tree. So what we're going to do, we take any given unicyclic graph, like this one right here. Here's our G. It has a cycle over here on the right, and we'll station a cop on the cycle. What does that mean? Well, we'll just pick some vertex of the cycle. We'll put the cop on it. That's the vertex. And we can notice here that if we do place this cop on this vertex and we station the cop there, to station them there, I mean it just sits there for the whole game. And if the cop's sitting there, it makes both of the edges that are adjacent to the cop useless for the robber. If the cops wanted to use those edges, they could, but they don't have to. So we can just act like this edge is gone. That edge is completely useless once the cop is sitting there. So the cops can just pretend it's useless, the whole team of cops, and the robber can't use it, because if the robber used that edge, it's guaranteed that the robber would get captured. So for the purposes of the robber, this is a tree. It's now a tree for the robber. And we obtained this tree by starting with this graph G of order n, and we just removed an edge from G. And we kept all the vertices in it. We just removed an edge from the cycle. So we have a tree of order n there, and the cops, besides this cop that's stationed on the cycle, and the robber will just play the game on the resulting tree. And so we know that the throttling number of any tree of order n is at most t of n. So the throttling number of this graph G is going to be at most T of n for the game that's played on this resulting tree once we remove that edge. And then the plus 1, where's that plus 1 from? Well, that plus 1 is just from the cop that we stationed here. So the stationed cop, that's what's giving us the plus 1. So we get T of n for this tree that we made of order n. So we were given this unicyclic graph G, and we just turn it into a tree of order n. And so that's where the T of n and the upper bound's coming from. And that plus 1 is just that cop that's sitting there on the cycle. So that's how we get that upper bound. So the proof is pretty much just drawing a picture. And I have a problem for you to think about, which is closely related to this. So let's say we try to generalize it. So we have some connected graph of order n, which has k cycles. And that is what we'll call k-cyclic. So k-cyclic, intuitively, it means has k cycles. So if we have a graph G, a connected graph of order n with k cycles, a problem for you to prove that the throttling number of G is less than or equal to T of n plus k. And so you can think about it like this picture that I've drawn here of a G. This one has 2 cycles. We want to prove for this one that the maximum throttling number is at most T of n plus 2. So can we imitate what we did on the last slide and generalize it to have more cycles than just 1? So I'll let you think about that. So a few slides ago, we were talking about how all of the families of graphs that the original investigators considered when they defined the throttling number, all of those families, they noticed that the throttling number had an upper bound of big O of square root of n. And all these families were connected. And of course, if we were considering disconnected families, like if we took some empty graph of order n where all the vertices are isolated, then for this graph, if this is our G up here, the throttling number of G would equal n. So if you have an empty graph of order n, a graph of order n that doesn't have any edges, then you have to use n cops. And all of the cops will capture the robber immediately. So there don't have to be any turns of the game played. They're already, the robber's already on the same vertex as the cop before the game even starts. So for these graphs, we can see that obviously they are not going to be big O of the square root of n. So clearly, if it's disconnected, that we can make many examples when it won't be big O of square root of n. But for connected graphs, it seemed less obvious. It seemed like maybe it would be true that the throttling number would always be big O of square root of n for connected graphs of order n. Notice that if true, this would have implied Manuel's conjecture. So this problem, you could think of it as like a strengthening of Manuel's conjecture if it was true. The problem is that it is it's false. So it's not true. And in fact, it's very not true. So there's a family of connected graphs of order n for which their throttling numbers are on the order of n to the 2/3. So it's not just that the big O of square root of n is false. It's that it's false by n to the 2/3 minus 1/2. So 2/3 minus 1/2 is 1/6. So there's an n to the 1/6 gap with how false that question was. So we're going to look at how can we build this family of connected graphs that have really high throttling numbers. And the way we build them, it's pretty intuitive. We use graphs that have high cop numbers, and we combine them with another graph, which is more simple. So we'll take two ingredients for this construction. We will start with the cycle. The cycle has order n over 2. And we take n to the 1/3 copies of this graph, h sub n to the 2/3 over 2. And h sub I right here, this is the graph of high cop number. So for example, the Pursuit construction that we discussed on a slide in the earlier video. So Pursuit showed that the cop number is greater than or equal to square root of n over 8. I think this bound is for n at least 72. So we can use Pursuit's construction from that paper, and we'll define hi to be the graph of order I with the cop number at least square root of I over 8. And so the specific hi that we're taking I equals n to the 2/3 over 2. And we're taking n to the 1/3 copies of this hi. So here's our copies of hi. And over there is our cycle of order n over 2. And we're just going to place these copies of hi around the cycle at nearly equal intervals so that they're only connected to the cycle by a single vertex. And so here's how we'll place them. And our cycle had order n over 2. And remember, we had n to the 1/3 copies of hi. So n to the 1/3 copies of hi. And the cycle was c of n over 2. So it had n over 2 vertices. And so if we look at the length of the intervals between these copies of hi, the length of the interval is going to be approximately n over 2 divided by n to the 1/3. And so you see that's how we got the n to the 2/3 over 2 right there. And again, I'll mention that the copies of hi, they're attached to the cycle at only a single vertex. So now we split the proof into cases. Case 1, if we use at least n to the 2/3 over 4 cops to throttle this graph. So when I mean throttle this graph, I mean n to the 2/3 over 4 cops to capture the robber. So if we use at least that many cops to capture the robber, remember the throttling number includes the number of cops plus the capture time. So if we're using at least that many cops, we already have the throttling number at least on the order of n to the 2/3 because that's on the order of n to the 2/3 cops. So that already gives us the omega of n to the 2/3 lower bound if we're using at least that many cops. So this is the easy case. The more interesting case is when we use fewer than that many cops. So if we use less than n to the 2/3 over 4 cops to throttle this graph, then we can define these sectors. What is the sector? Well, the way I've drawn it here, we can define sectors for each of these copies of hi. And the sector will consist of the copy of hi and all the vertices on the cycle that are closer to that copy than to any of the other copies. So here's a sector, here's a sector, here's one. So I'll just draw all the sectors like that. So each of these is a sector. And if we're using less than n to the 2/3 over 4 cops to throttle this graph, and we know the number of sectors is n to the 1/3 because we said that there was n to the 1/3 copies of hi. So if we have n to the 1/3 sectors and we're using fewer than n to the 2/3 over 4 cops to throttle this graph, then there's some sector that has fewer than n to the 2/3 over 4 cops divided by n to the 1/3. So if there's fewer than this many cops, then some sector has at most the average, because the average is going to be the total number divided by the number of sectors. So if the total number is at most this, then some sector is going to have at most this. And so we get n to the 2/3 over 4 divided by n to the 1/3. And that means that some sector has fewer than n to the 1/3 over 4 cops at the start of the game, because this is exactly n to the 1/3 over 4. Now, what is the problem with that? Well, the problem with that is the lower bound that we had on the cop number for these graphs h sub I. So h sub I right here, it was a graph with c of h sub I greater than or equal to the square root of I over 8. So when we look at c of h sub n to the 2/3 over 2, this is going to be greater than or equal to the square root of n to the 2/3 over 2, and then divided by 8. That gives us the square root of n to the 2/3 over 16, and that's n to the 1/3 over 4. So we know that these HIs have cop number at least n to the 1/3 over 4 when the I equals n to the 2/3 over 2. So if their cop number is at least n to the 1/3 over 4, and we know that there is some sector with less than n to the 1/3 over 4 cops at the start, then that means for the initial position, after the cops choose their initial positions, the robber will just start on the copy of h sub I in the sector with the fewest number of cops. So this sector S up here with fewer than n to the 1/3 over 4 cops at the start, the robber will just start in that sector on the copy of h sub I. And since that copy of h sub I has fewer than this many cops, the robber can just stay safe on that copy until some cop from outside of the sector reaches the copy. So the robber, I've drawn it here. So here's the safe sector. That's the safe sector where there's too few cops. So there's fewer than n to the 1/3 over 4 cops in that sector. And so the robber just goes on the copy of HI in that sector. And the robber is safe on that copy until some cop from outside the sector, like some cop from out here, reaches that copy of HI. And remember, the distance right here, so outside the sector to the copy of HI. So we know that our cycle was a C n over 2. And the distance between the copies of HI, we said the length of these intervals. So this interval right here, we said there was n to the 1/3 copies of HI, and the total length around the cycle is n over 2 because it's order n over 2. So we do n over 2 divided by n to the 1/3 to get n to the 2/3 over 2. That was the length of this interval right here, n to the 2/3 over 2. So that means that this length right here, this is n to the 2/3 over 4. So a cop from outside the sector reaching the copy of HI has to travel at least n to the 2/3 over 4. And traveling n to the 2/3 over 4, that takes big omega of n to the 2/3 turns. And remember the throttling number, it's summing the number of cops you use plus the number of turns it takes to capture the robber. So in this case, if this cop from outside the sector takes at least on the order of n to the 2/3 turns to reach the copy of HI where the robber is sitting on, and when I say sitting on, that's the wrong word because the robber can be moving around that copy of HI. But regardless of how they're moving, they can stay safe because that copy has too few cops on it until the cop from outside the sector reaches it. And that cop from outside the sector is taking omega, big omega of n to the 2/3 turns to reach that copy of HI. And big omega of n to the 2/3, that's the lower bound we're trying to prove. So the distance that cop from outside the sector has to travel to reach the copy of HI in order to capture the robber, the distance is at least big omega of n to the 2/3. And that gives us the lower bound. So with the first case, when we used at least n to the 2/3 over 4 cops, we got the lower bound on the throttling from the number of cops. And the second case, when we use fewer than that many cops, we get the lower bound on the throttling from the number of turns that it takes to capture the robber. So the cases are based on the two different parts of the definition of throttling, the number of cops and the number of turns. And each of the cases uses a different part. And one interesting thing about this proof is that the proof can give an even better result if you can find a better construction for the graphs HI. So the graphs HI we were using the construction from Pralot and the other people who proved big omega of square root of n lower bounds on the COP number. But if you could find some family of connected graphs where the COP number has a lower bound of big omega of n to the alpha, for some alpha that's greater than 1/2, then you get an even better lower bound on the maximum throttling number of connected graphs of order n. So the bound that we got was big omega of n to the 1 over 2 minus 1/2. And that's equal to big omega of n to the 1 over 3/2, which is n to the 2/3. But if you could improve that to a higher value of alpha, then in general, in terms of alpha, the lower bound could be written like this: omega of n to the 1 over 2 minus alpha. And before we finish the video, I just want to mention some interesting open problems related to these topics. And some of these problems might be approachable because most of these are pretty new problems. So one of the problems, which I think is interesting, is what is the maximum possible throttling number of a tree of order n? This is a problem that I've worked on some. And there are bounds on this maximum, but it's pretty wide open what the exact value is. So the best known lower bound on this maximum is 1.45 square root of n. And the best known upper bound is square root of 14 over 2 square root of n plus big O of 1. So that big O of 1 is just a constant additive factor. And I'll mention that this lower bound here, that's just from a spider. It's from a spider that has a single really long leg and then a bunch of shorter legs. All the shorter legs have the same length. So you can get that lower bound on the maximum just with the spider. And the upper bound right here, it uses an argument where you take a tree and you split it up into sectors whose sizes are within a factor of 2 of each other. And the sectors have very little overlap. And if you want to know more info about that, you can ask me. I proved both of these bounds. I'll also mention one other thing. So the best known bounds, the best bounds that are posted online are these bounds. This lower bound recently has actually been improved a little bit. So one of my collaborators found a way to improve that lower bound to approximately, I think it's now approximately 1.47 square root of n. And the method that he found to improve this lower bound was an automated search. So for now, it seems like the best known lower bounds are going to be found by automated search, unless someone finds a totally different way to prove the lower bounds. So the lower bounds that are being constructed right now, all of them are certain kinds of spiders, but they're more complicated spiders than the one I drew up here. So in order to find them, my collaborator did an automated search. So the best known lower bound, it is a little higher now. It's up to around 1.47 square root of n, but there's still a huge gap between these bounds because this bound is like 1.8 something square root of n. Also, another interesting open problem is What's the maximum possible throttling number of a spider of order n? This one, the best known bounds, it's the same situation here where the lower bound has been improved a little bit recently. So this is now up to around 1.47 square root of n. The upper bound for spiders is lower than the upper bound for trees in general. So for spiders of order n, an upper bound of square root of 3 square root of n plus big O of 1 is known. So square root of 3, this is 1.7 something, so a little lower than the upper bound for trees in general. And if you want to know more info about this, this is also a bound that I proved, so I can tell you about that. Or you can look at the paper online. If you look up my name and the word throttling on Google, it'll be pretty easy to find. And this problem is, I think, even more interesting than the problems up there. So what's the maximum possible throttling number of a connected graph of order n? So the construction we talked about over the last several slides with the copies of HI and the cycle, that's related to this. So we know that the maximum possible throttling number of a connected graph of order n is at least omega n to the 2/3. And in the same paper where we proved that omega of n to the 2/3 lower bound, we also proved an upper bound on this maximum. We proved that it is sublinear. So like the COP number is sublinear, the throttling number is also sublinear. So you can look in that paper. And that paper, I was writing it as like BBB, CEG, HPR. Maybe you were wondering what did that mean. This was a paper that had 9 authors on it. So each of those letters is a name of one of the authors. That is me. So in that paper, we have both this big omega of n to the 2/3 lower bound and the big O of n to the 1 minus little o of 1 upper bound. So that's just a barely sublinear upper bound. And you can see there's a huge gap between these bounds. The gap is approximately n to the 1/3. So it would be very interesting to see what is the maximum possible throttling number of any connected graph of order n, or at least to get some sharp bounds on it. But this problem, it seems like it's probably as difficult as Manuel's conjecture. So if we were able to figure out the maximum possible throttling number of a connected graph of order n, it seems likely that we would be able to get the maximum possible COP number of a connected graph of order n first. So this question may be more difficult than C of n, which is Manuel's conjecture or Manuel's problem. And here's another one that is pretty interesting. Maybe not necessarily as interesting as the one before it, but I think it's also very interesting. So for planar graphs, so we know planar graphs, there's that famous result that the COP number of planar graphs is less than or equal to 3. So can we say is the throttling number of planar graphs big O of square root of n for planar graphs of order n, and this of course should be connected planar graphs of order n, because if it was disconnected, we could take an empty graph of order n with all isolated vertices. Of course, that throttling number will be n. And another natural one that you could look at is the throttling number of Copwin graphs. So Copwin graph has to be connected. And is this big O of square root of n? So there's a lot of families of graphs where it's not known whether the throttling number is big O of square root of n, but it's conjectured that it is. And so these two at the bottom are some of them. And there's other families of graphs that we haven't discussed these families, so I'm not mentioning them, but they're also families you consider which are open for this problem. So that's just a list of interesting open problems, and some of them might be pretty doable because these problems have only been open for a few years. Throttling was only defined in the last few years. So hopefully some of these are interesting, and thanks for watching.